Okay, so continuing on in acids and bases, we're going to learn how to find the pH of various types of problems. And in this unit, there's lots of different types of problems, but they can be categorized into 4 types. We're going to go over the first 3 types today. All right, and some of these we already know because they've already been discussed, but we'll go over them anyways. All right, so the first type of problem that we're going to see is being able to find the pH of strong acids, right? Now, this is the easiest type simply because we know that strong acids dissociate completely. Therefore, whatever the concentration of the strong acid is, for example, if it was HCl, because it dissociates completely, then we know that whatever it is also the molarity of the H plus ion, right? So literally, to find the pH, you're just taking the negative log equals a negative log of the H plus or whatever the strong acid is, right? Not much to it. You just take the negative log of the concentration. Same goes for strong bases, right? So HCl, HBr, HI, HNO3, all the strong HClO3, and then the sodium hydroxides, lithium hydroxides, potassium hydroxides. Although you have to be careful with diprotic acids, like this is not true for sulfuric acid. I know that's a strong acid, but it does not apply to sulfuric acid. You're going to see why in a little bit. Also, be careful about strong bases that have 2 hydroxides, right? So calcium hydroxide, you'd have to double the concentration of hydroxide first before you take the pOH of it. Okay. All right, so what's the pH of a 0.25 molar solution of KOH? Well, that's a base, so really what I'd be doing is be taking the pOH, so it's pOH, it's the negative log of 0.25, which is 0.602, so the pH would be 14 less that, so 13 point, let's just call it 13.0. Okay, no big whoop. Strong acid, strong base, not even really a problem, right? Okay. Let's talk about weak acids. And you have already done some of this, but we'll go over it formally. When you have a weak acid, you are determining the concentration of H plus before you can determine the pH. So you need to follow all the steps that you would need to do in any kind of weak acid equilibrium. Right? In the case of a weak acid, X is what we would consider to be H plus, and therefore once you find X, you're taking the negative log of X, and that's how you get your pH. So let's say we have acetic acid, HC2H3O2. I am writing this equation without water. Water is not required because if I did include water, it just means I'd be forming H3O plus instead of H plus. But nothing really would change because we know H3O plus and H plus are considered the same concentration. All right, so what do we have? We got a 0.5 molar. And the Ka is known to be 1.8 times 10 to the negative fifth. So our law of mass action is the products over the reactants are set equal to the equilibrium constant. All right, in this case, the subtraction of X can be neglected. And for X, we get a value of 0.003. So if that is this, then we know the concentrations of those, and the concentration of 0.5 would not change appreciably. 0.5 minus 0.003 technically would be 0.997, right? Which, you know, if you want to round or not, stays as 0.5. All right, so the negative log. You're looking at a pH of about 2.5. Let's see how many sig figs can we use here. Ka only gives us 2, so 2.52. That is your standard weak acid equilibrium problem, right? If this were a base, right? If this were a base, so let's do one as in a base just because you should be able to do both. Okay, so let's say we have some fictitious base, we'll call it Q minus, right? So Q minus, here's our hydrolysis equation. Nothing registers underwater, of course, it's liquid. Let's say we have a concentration of 0.5 like the other one. Right, so your setup is largely the same. Let's say the Kb for this base was, bless you, 3.5 times 10 to the minus 7th. Let's just go with that. Okay, so what is the pH of this base, Q minus, which is a negative ion? Well, you're kind of doing all the same stuff that you've been taught. We're going to just ignore the x. There's no real reason to use a solver here, so just multiply both sides by 0.5 and take the square root. Okay, so x is 4.2 times 10 to the minus 4. Therefore, to find the pH, the negative log, I can't find the pH directly. I have to find the pOH first. So that's going to be 3.38. So then the pH can be found, 10.62. Okay, weak acid, weak base equilibrium. It's just an equilibrium problem with a pH problem tacked on at the end. Okay, so this is stuff I think that you're fairly comfortable with, right? So let's move on. Okay, weak acid mixtures. In real life, most solutions that you use in commercial products and that you will encounter are going to be mixtures of a whole bunch of stuff. You know, even from something as simple as like apple juice or Sprite or Sierra Mist or, you know, Gatorade. There's more than one weak acid in all of these solutions. So they're mixtures of them. And each weak acid has its own Ka value. Okay? So the first thing that you must do, which species is the most influential? And by most influential, what that means is which one has the highest Ka value? Because the weak acid with the highest Ka value is going to dictate what happens in solution. Right? It's got the greatest tendency to react. So it sets the tone and everything else kind of follows after it in its wake. And once you figure out which one has the highest Ka, then you go about solving this just like you would any other equilibrium problem. And then when you're done with that, we might need to do a secondary equilibrium problem for the second strongest acid. And then a third if there's three, and so on. All right, but you always start with the one with the strongest value, with the highest value. Okay, so let's look at this example here. 0.75 ammonium nitrate. Remember that ammonium is NH4 plus. And hydrogen sulfate. So hydrogen sulfate, NaHSO4, but really what we're concerned with is this ion because the sodium is a spectator. Just like in ammonium nitrate, we don't care about the nitrate because the nitrate is inert. So I have two ions. I need to figure out what their Ka value so I know how to proceed. Where could I possibly find such information? Oh, how about a helpful Ka sheet that is posted in the unit folder? It's called the Ka-Kb sheet. It's a very imaginative name, all right? So I had two acids, and let's see, is ammonium here? Oh, ammonium is not here. Oh, but look what is. ammonia is here, but that's a base. How is a base and its Kb value going to help me in my quest to find a Ka value? How do I find that? Ferris? Bueller? Bethany, how do I do this? Oh, okay. Okay, I can use KW. Let's do that. So, here's what we know. We know the Kb for NH3 is equal to 1.8 times 10 to the minus fifth. But the conjugate acid is NH4 ammonium, and that's what we're dealing with. So because Ka times Kb is equal to Kw, this will allow me to use the known Kb to find the Ka that I'm in need of. So Ka is equal to Kw over Kb. So let's do that. Kw, of course, 1 times 10 to the minus 14th over the Kb, 1.8 times 10 to the minus fifth. Should be about 5.6 times 10 to the negative 11th. Let's just double check. Tenth. Okay, this is my Ka for ammonium. Guys, if you ever need a K value and you don't have it directly, check the sheet. Just pull it from there. All right, sodium hydrogen sulfate, HSO4. I don't know that off the top of my head. I mean, I do, but you don't. So let's look it up. Okay, so HSO4. Anyone see that on here? Here it is. Yep. 1.1 times 10 to the minus 2. Okay, so that's literally there. So, in other words, 0.011. That's kind of high for a Ka. Have you noticed that all of the K values and Kb values you've seen are like 10 to the negative 5th, negative 8th, negative 10th, right? This 10 to the negative 2, that's really high. All right, so bisulfate is what the other name this goes by. This is like the king of weak acids. All right, Ka of 1.1 times 10 to the minus 2. You won't find, I don't think you'll find a weak acid with a Ka higher than that. This actually falls into a category which is in some textbooks called a moderate acid. Because they think it's too strong to be considered a weak acid, and they have a point, but it's just confusing. Now we have to go into like 3 categories of acids, and who wants to do that, right? The point is it's not a strong acid, and it has a Ka value, and that's what it is. All right, I have two Ka values. I need to start my equilibrium problem. So you start with the one with the greater value. I'm going to add a page here because we'll need more room. Okay, so HSO4. All right. Initial concentration of the bisulfate is 3 molar. And this step is fairly straightforward. All right, I am not going to ignore the subtraction of x in this case. I'm going to leave it in. What do you guys get for a value of x?
0.176.
Okay. All right. So, at equilibrium, my concentration of H plus is 0.176. And just, out of curiosity, if I had to stop and calculate the pH right now, what would that pH be? I'm just going to take the negative log of x. All right, and so the pH as it stands would be 0.754, okay? Currently. All right, that was the first and strongest equilibrium. This was a mixture of two weak acids. That was the first. Let's now carry into the secondary equilibrium, which was for the ammonium. But here's the thing. Remember when you had an equilibrium and there was some ion that was common to both equilibria? So we have just established the concentration of H plus produced from the first equilibrium is a concentration of 0.176 molar. And because the priority, the sequence of dissociation goes strongest and then weakest, this secondary equilibrium now has to establish itself in the wake of the first equilibrium, which produced 0.176 molar H plus, which means this is a common ion problem. This is the initial concentration of H plus that is present in the secondary equilibrium. Okay. All right. So what was where's my ammonium concentration? 0.75. 0.75. Okay, nothing there. Do I know which direction this equilibrium is going to proceed? There's something on the right side. Will this equilibrium go forward or will it go backwards? I can see why you said that, but the fact is there's still a zero, right? And in order for an equilibrium to be established, you have to have something on both sides. So this direction must go forward. We will be adding X to the product side, subtracting it from the reactant side. Okay, those are my equilibrium variables. Now I use my law of mass action. So the Ka we said was 5.56 times 10 to the minus 10, and it's equal to products at equilibrium over reactants at equilibrium. Okay, and this is definitely a job for solver. Yes. Oh, that. Oh, yeah, you're right. Plus, yep. Thank you. Okay, so let's pop that in there. Okay, so we get the value of X, 2.37 times 10 to the minus 9th. Okay, let me ask you this. When I add 2.37 times 10 to the negative 9th to 0.176, how much does the value change? Based on how many sig figs were allowed. It doesn't even change. Look how tiny of an addition that is. Okay, so the secondary equilibrium did not contribute much. Okay, so the pH as calculated before is still the pH that we would have at the end. So technically speaking, we're still taking this and putting it in here, but the X value is so small, the number doesn't even change, and the pH is going to be 0.754. once equilibrium is established. Okay. So you might ask, well, is there a point in carrying out the secondary calculation? Why did we do the secondary equilibrium? The reason is this allows us to solve for the calculations of the other reactants and products if needed. Like if the question was, what is the concentration of NH3? The only way you would find the concentration of NH3 is if you went through both equilibria. You couldn't get it from the first. You would have to carry out the second because you need to find out what X is from the second equilibrium. Does that make sense? Okay. All right. So this is a weak acid mixture problem. Anytime you have a mixture of weak acids, the first thing you do is what? Find the K's and solve the problems in order of K's. All right. Okay. Saying K a lot. Percent ionization. We went over this briefly, right? Whenever you're asked to find percent ionization, remember that it's just the concentration of the H plus at equilibrium over the concentration of whatever the original acid was initially times 100. Okay? So if you need to find percent ionization, right? Of course, you could work this backwards. What if I told you, such and such is 5% ionized, and here's the concentration of H plus? You could use that to find the initial concentration of the acid, right? Just algebraically find it. Okay. Let's solve the percent ionization for two different scenarios. All right, so here we have a 1 molar acetic acid solution, and here we have a 0.1 molar acetic acid solution. So one is 10 times more concentrated than the other. Let's go ahead and see what we get. All right, so the H plus concentration of 0.00424 over an initial concentration of 1 molar times 100%. Okay, this will be 0.424% dissociated. Okay? But let's do this again. And here we have a 0.1 molar solution, and they're telling us the pH. If they tell us the pH, it's no big deal. We know that we can find the H plus. So let's do that first. All right, so the H plus concentration is 0.00129. So find percent dissociation, 0.00129 over 0.1 times 100%. And now percent dissociation is 1.29. Interesting. It's not the same percentage. Observations. What happened? What caused the difference in the percent dissociation? This was the same acid. This was acetic acid in both instances. But why is there a different percent dissociation? You have different concentrations. So the trend is the more dilute the concentration, you increase the percent dissociation. And logically, if you think about this, the less acid there is, then the less likely the ions will bump into each other again. Right? So the lower the concentration, the greater the chance the ions will stay separated, right? Hence the higher percent dissociation. If you have a really concentrated weak acid, it's constantly bumping. The conjugates are constantly bumping into each other over and over and over again, right? So that will reduce the percent dissociation. Okay, try this problem right here. What you know is that the concentration is 0.1 molar. That's the initial concentration. You know it's 2.53% ionized. What is the pH? What is the Ka? So take a second and see if you can set that up and figure it out. For you don't know the formula for benzoic acid, just use HB. So if you know it's 2.53%, just work the equation backwards, set up what percent ionization or dissociation looks like, divide both sides by 100, and then rearrange yourself for what the H plus is. The H plus will be 0.00253, and we're going to go use that here. And then subtract that from this side. So that's going to be 0.0975. Okay, so the Ka would be 0.00253 squared over 0.0975. So Ka is 6 points. Ooh, got a little rough here on the initial sig figs. I'm gonna falsify this and say this was 0.10. All right, I'm gonna retcon it a little bit. So 6.6 times 10 to the minus fifth is the Ka, and the pH at equilibrium is just the negative log of 0.00253. .60. All right, percent ionization, no big deal, okay? All right. All right. So we already touched upon common ion problems, so let's do it again just to make sure we know how to handle it. Okay, so let's suppose we are mixing a solution of nitrous acid, HNO2, and KNO2. The KNO2 being a salt, the potassium is of no consequence. The point is you're mixing NO2 minus, right? These are the two things that are being mixed. Okay, that's what's in. So if we write out an equilibrium expression, we have both reactant and product present initially. So remember, when you have a common ion, the typical tendency is to reduce the forward reaction, right? If your common ion is a product, then you're going to reduce how much the reaction moves forward, okay? So the equilibrium tends to shift it to the left. And how will this affect pH? So let's go ahead and carry this calculation so we can answer that question. All right, so here's our table. Because we have a 0, we know that something must proceed to the right. All right, so flush this out. And our expression is going to be the same as you expect, products over reactants. So with substitution then, 4.0 times 10 to the minus 4 is equal to x times 0.2 plus x over 0.1 less x. Okay, so if we ignore the effect of the x's, just to simplify this, x is 2.0 times 10 to the minus 4. So the pH is going to be 3.70. Okay, does everybody understand how this problem was set up? You had initially you had both the weak acid and you had its conjugate base present at the beginning. Okay? Now, be aware, in the future, should you have a problem like this again, you have to be really careful about the wording. Here, you are given the molarities of the solution as it was ready to start. But what if I told you another scenario where you had to measure out and add a certain amount of this and add a certain amount of this? Realize then that the two would dilute each other. You would have to recalculate what those initial concentrations are when you put them in here. Okay, so just be careful, right? In this problem, the molarities were ready to go, but it won't always be the case. All right, so that's a lot of space there. Okay. Yeah, this will be the last problem for today. The polyprotic acids can furnish more than one proton, right? We talked a little bit about these. They're, when you have like H3PO4, for example, that's a polyprotic acid, right? They always dissociate in a stepwise fashion. The first proton is the pH determiner, okay? And that is because of this. In a polyprotic acid, you will have multiple Ka values. I'm going to switch over to look at that sheet here for a second. If we look back at our sheet, okay, everyone see phosphoric acid right here? So do you see how it's got H3PO4 and the Ka is 6.9 times 10 to the minus 3? But then it gives you a second Ka, and that Ka is H2PO4 minus. That's the secondary dissociation, meaning that is the dissociation after the first H plus came off. Look at the difference between the Kas. 6.2, 10 to the negative 8th. That's a big difference. And then below that, HPO4 2 minus, the Ka is 4.8 times 10 to the minus 13th. Whenever you have a diprotic or a polyprotic acid, the first dissociation is always the strongest. And then if there's another one, it's going to be weaker. And then if there happens to be a third, it's going to be the weakest. Okay, that is important to note because that follows suit with what we talked about in the examples we saw earlier. Okay, so I'm trying to figure out this. I want to know the pH of 3.5 molar solution and the equilibrium concentration of all species. Of all species. What does all species mean? Well, we have to go through all three equilibria to find out. So here's the first. All right, so the concentration, 3.5. This one is straightforward, just like you would expect. So Ka, the first Ka1, so what do we get? All right, so hopefully you got 0.158 for the value of x. Okay. We have, in the process of doing this, we have just created H2PO4. So let's now calculate the H2PO4 equilibrium. The products are H plus and HPO4 minus 2. What do I carry over from the first problem into the second? What values? Yeah. Didn't we make H2PO4? We did, and as a result, that is the initial concentration of the secondary equilibrium. And we also know that H plus was also made, and it's made in the same ratio, so we have that. What we don't have is the new product, HPO4 minus 2. We don't have that. It's okay. Let's carry out the math. Now we are using the secondary Ka. That color is not different enough. We're using this guy. Okay, so 6.2 times 10 to the minus 8th is equal to all of this. And if you are savvy with your equilibrium laws and rules, this drastically simplifies and you don't even need to do a calculation. Everybody see how the addition and subtraction of x can be neglected? And then really, then 0.158 cancels itself out. So that means that x is simply 6.2 times 10 to the minus 8th. Okay. Let's do the third equilibrium. HPO4 minus 2. The third and final proton comes off. The x value is the initial concentration of HPO4 minus 2. Let's put that there. Oh, nuts. I want to move that. Close enough. Okay. We have an H plus concentration somewhere. Which one? What do I use as my H plus concentration in this initial row? Is it 0? It is. Yeah, it's 0.158 because the first one made that much H plus, right? The second one, the H plus concentration was 0.158 plus the value of x, but the x is inconsequential to that magnitude, so it's still 0.158 here. Okay, and this is 0. The phosphate is 0. All right, and the third Ka, here, we'll use brown, right there. So 4.8 times 10 to the minus 13th is equal to all of this. Safe to say, the addition and subtraction of x's can be neglected. So this makes for an easier solve. All right. The value of x, 1.9 10 to the negative 19th. The concentration of phosphate in this successive ionization is exceedingly small. There is some, but it is small. So to answer the question, if you were to see one like this, make sure that you lay out the concentrations that were asked for and be clear about what you think they are. And, they also want the pH. All right, so HPO4. So 3.5 minus 0.158. Just going to call that 3.34 molar. All right, that's from here. H2PO4 is here. That was H2PO4. HPO4 minus 2 is from here, meaning it's still 6.2 times 10 to the minus 8th. And then PO4 was that. The pH is based primarily on H plus, which is 0.158. And that's 0.8. Rohan, question.
Would the concentration of H2PO4 would it be 1.158?
Sorry, what?
The concentration.
Oh, shoot. Yes. Yes. It was this one I was trying to move right. All right. That goes there. Thank you. 0.158. My bad. Okay. That was fun. Okay, so, is it hard? Are the individual steps hard? No. It's what's hard about this is the coordination and putting the right numbers in the right places when you start the problem. That's where the difficulty lies. And the more complicated it is, it just means more steps. It's not that the actual steps are difficult. It's just keeping track. Okay. Actually, we do need to talk about this. Okay, I was kidding about the last problem. This is the last problem because this is important. Sulfuric acid. It's a strong acid and a weak acid. What does that mean? Well, H2SO4 is a strong acid, but its conjugate, HSO4, is the weak acid. Right? We discussed the Ka value is known for HSO4 minus. It's 0.011. So here's the thing, right? When H2SO4 dissociates, it is a one-way dissociation to produce this. Okay? So if I were to write an ice table, which, for a strong acid doesn't really make sense, but I'm just doing it to demonstrate what the numbers would be. So if this is a 1.25 molar solution, 1.25, okay, that means the concentration of H plus is 1.25 molar and the concentration of HSO4 is 1.25 molar. Does that make sense? Right? Plus 1.25 plus 1.25 minus 1.25. There's nothing left of the original. And that's because it's a strong acid. That meets the definition. But to carry out the secondary step, HSO4 minus because this is a common ion problem, we carry over this value here, 1.25. We also carry this value here, 1.25, 0. And the Ka was 0.011, which is equal to 1.25 plus x times x over 1.25 less x. So what is x now? .0108 is x. And so the question is, what is the pH? Well, the pH would be based off of this value, because that is the final concentration of H+. So 1.25 plus 0.0108 is 1.26. So the pH will be negative log of that, which is negative 0.104. So If you ever had a question, can the pH be negative? Yes, it can. You can have a negative pH because remember the pH scale is a negative logarithmic scale. What is the pH of a 1 molar H plus solution? It is 0. Well, what if the concentration of H plus is greater than 1 molar? Then you get to negative. The pH scale is a construct. There's nothing saying that it's not possible to have a negative value. It's just a set of parameters that we designed to make number crunching more convenient. Okay? All right. That was for a 1.25 molar solution. What if we do this for a 0.125 molar solution? So a different concentration. Try to do this one smaller so it could fit everything. 0.12500 x 125 minus x. Okay. Wait a minute. Sorry. That's, what am I doing? We know this value. This was the strong acid part. This is 0.125. Okay. So, secondary equilibrium. All right. That's great. This will be a fun watch later on. Okay, so the value of x now is 0.00945. So what is the pH as a result of this equilibrium? We are basing the pH off of the last H plus value that we got. So 0.125 plus 0.00945 is not insignificant. It's 0.134, so the negative log. Our pH is going to be 0.871. Okay, so here's the thing. The dissociation of the secondary reaction, which is the equilibrium reaction, doesn't change too much when in the presence of the strong acid. But when it's by itself, it produces more. It's just that in this scenario, the value of x is inhibited by the fact that we have an initial concentration of H plus that's so high. All right. Good stuff.